In this video, we are going to talk about graph colorings. Okay, so an M coloring of a graph assigns each vertex one of M distinct colors. So we are coloring each vertex some color, and in an M coloring, we can use M distinct colors. So when we do that, vertices that share an edge have to be different colors. Okay, so if such a coloring exists, then we say the graph is M colorable. All right, so let's do an example. Do the following graphs have a 3 coloring, and then do they have a 2 coloring? So in part 1, we have C3. So remember, this is a cycle with 3 vertices. So I got the cycle drawn twice. I want to ask, well, can I do this with 3 colors? Can I do it with 2 colors? So can I do it with 3 colors? So maybe I make this vertex at the top black, and then I make the one at the bottom left. Maybe I make this red. That's a fine color because these 2 vertices share an edge, so they had to be different colors. Now this third vertex shares an edge with the black one and with the red one, so it's got to be a different color from both of those. So maybe I can pick blue. So yes, I was able to do this with 3 colors. So yes, this is 3 colorable. It is 3 colorable. Okay. So now can I do it with 2 colors? Well, okay, yeah, I can pick any vertex to start with and just assign a color to it. So maybe I'll make this one black. Because this one shares an edge with the black vertex, it's got to be a different color. So maybe I'll make that one red. But now this third vertex, well, it shares an edge with the red one and with the black one. So, well, that means I can't make this red or black. This can't be red or black because it shares an edge with both of those. It's got to be a different color. So I'm forced to use a third color. So unfortunately, I would say no, this is not, it is not 2 colorable. Okay. Let's take a look at another example. What if I had a cycle with 4 vertices? So I first want to give you an opportunity to try this one. So pause it for a minute, see if you can do this with 3 colors, then see if you can do it with 2. Pause it in 4, 3, 2, 1. Pause it and try it. All right, so hopefully you did that. Hopefully you paused it and tried it. So can I do it with 3 colors? Sure. Yeah, I could make this black, and then the bottom one's got to be different from the black because they're connected. So maybe I make it red. This one's got to be different from the black one. So, maybe I use a third color because it says, can I do it with 3 colors? And now this bottom right one, it's got to be different from the red and different from the blue because it's connected to both. So I can make it black. That way I'm not using a 4th color. So yes, this thing is 3 colorable. Yes. Yes, it is 3 colorable. Awesome. Okay. So is this thing 2 colorable? Is it 2 colorable? Well, yes, as well. If I made this one be black, the bottom one could be red. When I think about this top right one, it just has to be different from the black one. I don't have to use a third color though. What if I just use red again? Because now the bottom one is connected to 2 reds, so it's got to be a different color. Well, I can make it be black. I don't have to introduce a new color needlessly. So yes, this is also 2 colorable. This is 2 colorable. Okay, so now I want to talk about a key theorem. So the big theorem of this video, which says that if G is a simple graph, that means no multiple edges, no loops, then G is bipartite if and only if G is 2 colorable. Okay, so let's recall, what does bipartite mean? So we talked about this in the last video. A graph is bipartite if I can split the vertices into 2 groups like this, such that any edge that exists in the graph will always connect one vertex in the first group with one vertex in the second group. If I can do that, if I can split the graph into 2 groups of vertices like this, then the graph is called bipartite. And as we saw in the last video, well, some graphs I can do this, they are bipartite, but some I cannot. Okay, so conceptually, one of the reasons why I might expect there to be a relationship between these 2 things is, well, bipartite involves splitting a graph into 2 pieces, and, well, 2 colorable has the number 2 in it. There's this 2-piece element involved. Okay, so let's dive into the proof. because I have an if and only if statement, we got to show both directions. So maybe I'll start with the forward direction. In the forward direction, I assume my graph is bipartite. So I'm going to let G, and because I want to be able to talk about the vertices and how I color the vertices, let me use my notation for graphs, where I have V for the set of vertices and E for the set of edges. Let my graph be bipartite. So I'm going to start off by saying that. And then on the side, I'm going to keep track of what it is that I want to show. So in this direction, I want to show that G is two colorable. I want to show that my graph is two colorable. All right. And I'm going to do a little bit of scratch work just alongside, on the side here. So if my graph is bipartite, what does that mean? Bipartite means I can split the graph into two groups of vertices. So maybe there's two vertices here, maybe there's three over here, such that any edge that we have connects the two groups. So maybe there's an edge connecting this one to this one, and maybe there's an edge connecting this one to that one, and also to the bottom one. And maybe this vertex here is isolated. That's okay. So that's an example of a bipartite graph. So is this going to be two colorable? Well, yeah. One of the things I can notice is, well, what if I just color all the things in the first group one color, like red? And then I color all the vertices in the second group another color, like green. Well, now any edge that we have always joins the two groups. So it's going to have one endpoint be red and one endpoint be green. That's going to be true no matter which edge I take, because any edge always joins the two groups. That's the definition of bipartite. Okay, so this picture in the scratch work helps give me the idea. So I'm going to let my graph be bipartite. So what does that mean? Then this means then there is a bipartition. Bipartition, that just means a way to split the vertices into two groups, is a bipartition, which I'll call V1, comma V2. Those are the two sets of vertices. Bipartition of V, the set of all vertices. And let's color the vertices of V1, one color, like red, and the vertices of the second group of V2, a different color, like green. Okay, and then just as we saw in the scratch work, what's going to happen now is, well, since my graph G, I'm given that this is bipartite. Since my graph is bipartite, well, any edge joins a vertex that's in V1, the first group, which is going to be red, with a vertex in the second group, with a vertex in V2, which is going to be green. So any edge that we draw is going to join a vertex in the first group and a vertex in the second group. So it'll always join a red one and a green one. But that's exactly what it means for the graph to be two colorable. So I can say thus, G is indeed two colorable. Okay, so that completes the forward direction. Now I need the reverse direction, which honestly is going to be really similar. Now I assume that G is two colorable. Let G which equals V comma E, let this thing be two colorable. Let this thing be two colorable. Okay. And let me just specify what the colors are. I can pick whatever I want, just any two colors, with colors red and green. With colors red and green. Okay, so now I just know that it's two colorable. What I'm going to do is I'm going to take all these red vertices and all these green vertices and then make them be the two groups that I would need for it to be bipartite. So I am going to let v3. I don't want to reuse the same variables that I had in the first part just because I don't want to necessarily assume that they're the same. Let v3 be the red vertices, and v4 be the green vertices. v4 be the green vertices. So I have these two groups of vertices. So since my graph is two colorable, I'm assuming now it's two colorable, that means any edge joins a red vertex, which happens to be in V3, that's the first group, with a green vertex. Any edge will connect a red vertex with the green vertex, because that's what it means to be two colorable. And we're saying the green vertices or vertices are in V4. So what we've just shown now is, well, any edge joins a red vertex with a green vertex. In other words, joins a vertex that's in V3 with a vertex that's in V4. But that's exactly what it means for the graph to be bipartite. So thus, what I can say is V3, V4 is, well, this is my bipartition. This is a bipartition of G, and that's what I wanted to show to complete this direction, to show that it's bipartite. So we've shown both of these directions, which means the result that we wanted to show, this if and only if statement, is true. So therefore, I'm running out of room here, G is bipartite if and only if G is two colorable. And that completes my proof. And there we have it. Okay, so one of the really nice things about this theorem is this connects two types of graphs that initially, where they're defined, don't necessarily seem to be related. And that's one of the really nice things that we see in graph theory, these connections between terms, because sometimes it's easier to work with one term than it is another. And it helps to build those connections so that we can work with the easier things.